Right, so here we go with CCEA, A2 Physics, Unit 2, Fields, Capacitors and Particle Physics for June of 2018. Let's get started. 2A, state Newton's law of universal gravitation in words. Okay, so this is straight book work. Between any two masses, there exists an attractive force which is directly proportional to the product of the masses and inversely proportional to the square of their separation. Part B1. CloudSat is a satellite orbiting Earth. It was launched by NASA in April 2006 to study the vertical structure of clouds and quantify their ice and water content. Use the information in Table 2.1 to calculate the orbital height of CloudSat above the Earth's surface. Okay, so we've got the mass of the Earth, radius of the Earth, and the gravitational field strength at orbital height. So that's our starting point. We have an equation for gravitational field strength. So G is G times the mass of the Earth over R squared, where R is the radius out from the centre of the Earth to the object that we're interested in, or the point in the gravitational field that we're interested in. Now, it's important to notice that R here consists of the radius of the Earth and the orbital height, and it's this one that we're trying to find. So this equation will give us this, and then we subtract off the radius of the Earth. So rearranging that, R is going to be the square root of GME over little g. So we now need to just sub in there and just put that through the calculator. So that gives us an R value. And we also need to take off this radius of the Earth, which is in kilometres, so just be careful about that. So if it's 10 to the 3 in kilometres, it's going to be 10 to the 6 in metres. So we do that subtraction and just respect our available significant figures at that point. Calculate the orbital period of CloudSat at this height. Give your answer in R's. Okay, so this is where we put the gravitational force equal to the centripetal force. So the force between the Earth and the satellite is G_me_ms over R squared, where me is the mass of the Earth, ms is the mass of the satellite. And then we also have that same force providing centripetal motion. So that same force is equal to the mass of the satellite times R times omega squared. So we can put those two things equal to each other. And we just collect terms and get omega squared on its own. So the masses of the satellites cancel, and we get an R going to the bottom line, so we end up with an R cubed down there. So we get GME over R cubed equal to omega squared. And omega can be represented as 2 pi over t, so omega squared is the same as 4 pi squared over t squared. So t will end up coming to the top line, and it will equal the root of 4 pi squared R cubed over GME. And that comes to 5914 seconds, so we need to divide that by 3600, and that gives us 1.64 hours. State giving a reason if CloudSat is a geostationary satellite. Well, it fails one of the basic criteria for being a geostationary satellite, in that it would need to have an orbital period of 24 hours. And there's several other things that need to be true, but if it doesn't have an orbital period of 24 hours, it would be impossible for it to be geostationary. And that's it.